Okay, formal definition of a limit. We kind of just barely started this yesterday, but we need more time. So let's take a look at this. What I want to do, I think a good way to approach this is to take our working informal definition of a limit, which is what we use, and let's talk about, how we add some teeth to this and make it more binding, make it more rigorous. So we're familiar with this. We know that the way we would say this is the limit of f of x as x approaches. Oh, I didn't mean infinity. That's supposed to be, that's the wrong one there. That's supposed to be not an infinity. As x approaches c, in this case, I guess, could be a, could be c, doesn't matter, is equal to L. What this says is, if f of x becomes arbitrarily close to a single number L as x approaches c from either side, then we can say that this limit exists, right? Okay, so let's talk about that language a little bit. That's good language. I mean, it's words that maybe you're not familiar with, but this is the kind of thing we do a lot in math and physics. We want to choose language that is unambiguous and means exactly what we intend it to mean, okay? What does this statement right here mean? If f of x becomes arbitrarily close to a single number L. Arbitrarily is a loaded word there. That's an important one. What's that mean? Suggestions. When we say something is arbitrary in regular language, what do we mean? Say it again. Okay, it gets close to it, but arbitrarily close meaning. Say it again.
Doesn't matter how close.
Doesn't matter how close. Meaning you could choose anything. It's vague. You could make the closeness as small or as large as you want it to be. I could make it. I mean, if I need it to be within a trillionth, well then this implies that I should be able to do that. Maybe I only need it within 100th of a unit, whatever my units are. Okay, but however close I need to get it, I should be able to do that, right? If f of x becomes as close as I need it to, arbitrarily close to a single number L, as x approaches c, that's pretty clear, right? As the ant is walking towards an x value of c from either side, then this limit definition makes sense. Okay, but this is a little too Englishy and not mathy enough for us, right? Saying as f of x becomes arbitrarily close to, or f of x becomes arbitrarily close to a single number L, as this happens, we got to be able to write that in terms of something that's more math-like, right? Some equations or some inequalities or something like that, right? So here's the picture that we draw. Okay, let's just see if this picture fits the bill. See if this does what we need it to do. Okay. If the purple function, we'll call that f. If an ant walks along this purple function and approaches c, does it exhibit the kind of behavior that we need? If we define some neighborhood of values around c, and this is called a neighborhood in math, kind of a friendly way to describe it. The width of the neighborhood is delta, okay, meaning that if we go from c minus delta to c plus delta, if we get within that neighborhood of values, can we guarantee that we will be within a certain target accuracy of the limit? Okay. In other words, let's just say a good way to describe this would be like with a tolerance in engineering. If we're making ball bearings and we need the radius of the ball bearing or the mass of the ball bearing or whatever, we need it to be fairly precise. If we need it to be accurate to within 1 mil, right? So 1/1000th of an inch, then can we do that by designing accurate enough equipment, for example? So we're going to say like epsilon here is going to be kind of our target accuracy. We've got to be plus or minus epsilon from our target value of L. Does that make sense? Okay. Could we do that by just getting closer to C? Okay. If so, then this works and the limit exists. Okay. Do you see that the width of epsilon is dependent on the width of delta for this function? Everybody see that? If I need to shrink epsilon, if I need a little more accuracy, then all I've got to do is get closer to c. See that relationship? Okay? So I can control how accurate I am in my approach to L by simply shrinking the neighborhood down, the neighborhood delta, right? Okay, so then this language, f of x becomes arbitrarily close to a single number L, we could say corresponds to this math statement, this inequality. All right, we talked yesterday just a little bit about what it means if we take an absolute value of f of x minus L. This is kind of where we left off yesterday. Everybody agree that that's describing the distance of f of x from L on a line, right? So if the distance between f of x and L is less than epsilon, then that means that we're between L plus epsilon and L minus epsilon, right? Epsilon could be whatever we choose. It's arbitrary, right? We can set epsilon to be whatever we need it to be, right? So this is our math way of stating f of x becomes arbitrarily close to a single number L by defining some value epsilon that represents the distance from L on the y-axis. That means that statement mathematically, right? As x approaches c from either side. Okay, well, that's how we'd say it right there, right? As x approaches c, then that means it's getting closer to c. And so once again, the absolute value of x minus c just represents the distance from x to c, right? If the distance between x and c is less than delta, then that means it's between c minus delta, c is the value I'm approaching, and c plus delta, right? If we can link those two things, then that works. Then the limit works. If I can shrink epsilon by shrinking delta, then we've got that kind of a limit relationship, okay? This is probably unique, or this is probably a little different than what you're used to. Formal mathematics like this it's not so much about solving equations. It's about formalizing a relationship between two mathematical expressions, right? And I don't know, you got to kind of think about this one a little bit. The good news is, I'm not going to do very much with it. It's not like we're going to spend a lot of time on this. This is more of a practical approach to calculus, first-year calculus, where we're just going to learn to solve some problems, and eventually we're going to learn to use calculus for some interesting kinds of, to solve interesting types of problems. Like we'll do some related rate stuff pretty soon, where we'll learn to do things like if we're inflating a spherical balloon, and we want to know what's the rate at which the radius is changing as we blow air into the balloon at a constant rate. When the radius is has a certain value, we can do that with calculus, right? We'll do things like we'll figure out for a profit function, if we come up with a profit function, where we can what price we can set our widgets at that we're selling, so we can maximize profit. We can do stuff like that. We can solve real important problems that only calculus can do. That's kind of more of the approach. But at the same time, I want to periodically just take a minute or a period and kind of talk about the formal parts of calculus that underlie all this. Now, if you end up being a math major, which hopefully you'll at least consider, or a math minor, then eventually you'll look at this in a little more detail, right? So, one other question then. So we said the red statement, red goes with red, right? So this is how we say f of x becomes arbitrarily close to L. That's related to the idea that x approaches c, right? We're within this neighborhood of values with delta. How come the 0? How come we're saying that the distance from x to c is greater than 0? It's non-zero. How is that consistent with what we always said about limits?
Can't be on.
Oh, the ant never actually steps on C, right? The limit does not depend on the ant ever getting there. In fact, the limit doesn't allow us to get there, right? The limit is just as we approach. So that has to be a non-zero value. It's a little, kind of a little fine print there. Okay, so then we can take this picture and we can take our informal definition of a limit and we can rewrite it in a way now that is more formal, but less useful at the same time. Let f be a function defined on an open interval containing C, except possibly at C. Well, there it is right there, right? So x is going to be, or the function is going to be defined on a neighborhood of values surrounding C, okay? And let L be a real number. Okay, so L is our limit. The statement, the limit of x as x approaches C equals L, means that for every non-zero value of epsilon, there exists a non-zero delta such that if x, the distance between x and C is less than delta, then the distance between f of x and L is less than epsilon. It's almost easier to appreciate how this works when you break it, when you pick examples where it doesn't work. If we went back up to this picture, think about the kinds of places where limits don't exist. And let's look at that. Would this work, for example, tell me, what is an example of where a limit doesn't exist? Large break in the function. Okay, let's try that. So if we have a function with a large break, like that, and let's call that C. So if we define some neighborhood of values then around C with width delta, well, what's our limit? We can kind of look on the graph here and see that the limit as x approaches C is different from either side, isn't it? There isn't a single value I could put over here where if I approach C more and more closely, if I shrink this neighborhood down, it's going to shrink the value of epsilon down around some answer. Not going to work, is it? As I approach the function from, or as I approach C from this side, I'm getting closer and closer to this value. If I approach from this side, I'm getting closer and closer to this value. Well, that doesn't look anything like that, does it? Right? I can't converge on some single value of L, right? Epsilon doesn't shrink down arbitrarily small, right? So it doesn't work here. This fails our formal definition. We can't make a connection between the width of the neighborhood and the accuracy of our approach to L, right? What's another place where it fails? Asymptote. It's an asymptote, okay? So if we have an asymptote, something like that, let's say. Okay, so this would be our value of C. As x approaches C, we're going to define some neighborhood of values. Well, as I approach C more and more closely, I'm not getting closer and closer to some value of epsilon. I'm just getting higher and higher on the function, right? In fact, it's exactly the opposite. As I get closer to C, the range of values surrounding epsilon actually gets bigger, right? But I'm certainly never going to get behavior like this, where as I get closer and closer, I converge on a single value again, right? So it breaks, doesn't work. Or if I had that oscillating behavior, same kind of thing is going to happen, right? If I have that oscillating, this is probably the easiest one to see in this case. If I've got some weird oscillating behavior, as I get closer and closer to this thing, well, it doesn't matter how wide my neighborhood is. As I get closer and closer, epsilon's not going to get any smaller, right? Epsilon, I'm stuck with, maybe that's you could say maybe that's arbitrarily like the center of the distribution, but epsilon never gets any smaller. I can get as close as I want to C, but this is never going to shrink, right? I can't get within the target accuracy that maybe I need, right? So it also fails. Okay, so now the next issue then is, how in the world would we go about proving that a limit exists using that definition? One sec. Hey. Cross-country bag in here. Where would you put it? Okay, hang on. Emergency. Yeah, it's handy. Let me see a unclaimed bag in here that could be a cross-country bag. I think so. Nope. Okay. Yeah. Okay. Yeah. Okay. Bye. Bye. All right. So how would we go about doing something like this then? What if we were trying to, let's take an example out of here. What if we wanted to, let's do two things. Do a problem like this. Step one is we're going to find L. Step two is we're going to define the maximum possible delta so that we can get within 0.01 of our limit, right? So how far does the ant, what's the biggest distance the ant could be from C on the graph so that he's within 0.01, his y value is within 0.01 of the limit, okay, for a function. So let's take something like okay, how about this? What if we say f of x is 2x minus 5 and c is 3? Okay? So first of all, let's just take, we know how to take the limit. That's no big deal, right? So L equals the limit of the function 2x minus 5 as x approaches c, which is 3, right? So what is our limit? 1, yeah. So that's L, isn't it, right? But if we want to get within 0.01 of L, which is 1, how close do we have to be to 3? Okay. How do you think we could show that? This is kind of cool. If we go back, remember, our goal here is to find a relationship between this and this, right? Okay, let's take. Okay, so let's take this guy. We'll copy that. We want to be able to go from something like that down to something like that. Mathematically, that means, can I start there and get to there? Well, what does that red statement look like for our function? So we've got the absolute value of f of x, 2x minus 5, good, minus L, which is 1, and that has to be less than epsilon, which we define as 0.01, right? Okay. Well, when we ask the math gods to go from there to there, their answer is always through algebra, right? So what can we do here? If we simplify inside the absolute value bars, what do we get? 2x minus 6. Okay? Is less than 0.01. Okay, well, our goal is to get down to this point right here, right? Which is the absolute value of x minus c, and c is 3, right? We want to get down to absolute value of x minus 3 is less than delta, right? How are we going to get from there to there? Ah, okay, good. We could factor a 2 out of this, right? Everybody see that? Maybe that'll show up better. So if we factor a 2 out, I could bring the absolute value of a product. Would you agree that's equal to the product of the absolute values? Okay. So I could write this as the absolute value of 2, which is just 2, times the absolute value of x minus 3, and that's less than 0.01. So what do I have to do then to both sides to isolate the x minus 3? Divide by 2. And if I divide by 2, I end up with absolute value of x minus 3 is less than 0.01 divided by 2 is what? 0.005, yeah. So what's delta? 0.005. See that? So it works. That indirectly proves that this limit exists because I just randomly picked a value of epsilon, and it output a value of delta. It didn't matter what value I picked. I could have picked a different value. I still would have, the algebra wouldn't have changed. I would have gotten an answer, wouldn't I? Does this answer make sense in terms of the shape of this line? And this is kind of a little bit above and beyond what the book does, but I want you to just see this relationship. If I graph this function, you'll get this. Could you have predicted this answer? What does this line look like? 2x minus 5. Well, it's got a y-intercept of -5, but more importantly, it's got a slope of 2. So it's going to look like that. Okay? So as x approaches, what am I approaching again? 3. Did I screw something up there? Oh, the slope is 2, not 1/2. So -5, yes, it looks like that, doesn't it? Okay. As x approaches 3, we're approaching a y value of 1. Okay, but why is it that delta is half as big as epsilon here? Slope is 2, right? Does that make sense? So for every step the ant takes to the right, he's moving up 2, right? Doesn't that make sense then if I go back to our picture? That if the slope is 2, doesn't that mean that epsilon is going to be twice as big as delta is? Because every time the ant takes a little step to the right, the vertical movement is magnified because the slope is greater than 1. Right? See that? Okay, so this really isn't surprising that we get this result. Right? Okay? Let's do something slightly different with this. Let's take, how much time we got? What are we at here? Oh, good, 3:10. Okay, so now let's not take a specific example like that, where I'm hand-picking a value of epsilon. Let's not specify epsilon, and let's just use the formal definition to prove that a limit exists. So let's say something like this. Now we've got, and by the way, the formal definition sometimes is called the epsilon delta definition of a limit. So let's prove that the limit of 3x minus 2 as x approaches 2 equals 4. Okay, let's prove that that limit exists. And you might be thinking, well, why? I mean, it seemed pretty clear when we talked about this before that if we want to know where the ant thinks he's going to step and it's a function like this, let's just find out where he's going to step and why the hassle? Okay, but once again, if we want to make this absolutely rigorous and formal, we have to show that this function, when I take a limit, obeys the behavior described by the formal definition. Okay? So we can see pretty easily that 4 is the answer, right? That's the limit. Okay? Let's do the same thing we did last time, and let's start off with our definition of epsilon and see if we can turn that into a corresponding definition of delta. Okay, so what is our definition of epsilon going to look like for our function? So if we're going to start here, so it's red, what do we get? Absolute value of, okay, good, there's our function, right? Taking the limit of f of x minus L, which is our limit is 4, is less than epsilon, right? And we want to turn that into something like this. Okay, well, we can kind of look ahead a little bit here. We know that this is going to end up looking like absolute value of x minus, let's see, 2, good, is less than delta, right? And the non-zero part, that's just part of our understanding of what a limit is. We can always stat that. Right? Okay, so we got to get to something like that. So what are the steps? Okay, so good. Combine like terms. Good. So absolute value of 3x minus 6. Take out a 3. We can factor out a 3, right? So we get absolute value of 3 times x minus 2. Absolute value of 3 is 3, right? And so we end up with, if I divide both sides by 3, absolute value of x minus 2 is less than epsilon over 3. Well, that's just delta, isn't it? Right? Isn't that delta? Because that's right. That's how we define the neighborhood. The absolute value of x minus c is less than delta, right? That's what delta means. The distance between x and c. And so that's saying the distance between x and c is less than that value. So that's delta. And so we end up with the relationship delta equals epsilon over 3. QED. We proved it, right? There is a tie between delta and epsilon. I could make epsilon arbitrarily small, and I could always define a neighborhood with this relationship narrow enough to get us within that target accuracy. Tells us how close, in terms of whatever I specify for epsilon, delta is just telling us how close that ant has to get to C to get within that epsilon range. Right? See how that works? Yes, sir.
So it doesn't matter, as long as you can show a relation between them within the bounds of the definition of function, that works.
Exactly. Yeah. As long as you can come up with some relationship like that, it's solved, right? Now, the problem is, if you can't do that, right, which we couldn't do, for example, if it was asymptotic, right, then it wouldn't work. If we tried to do something that was asymptotic, then we're going to end up getting some answer like we're going to divide by 0, which is going to produce an infinity or something. And we're not going to get a relationship like that. Okay? So, I mean, like I say, don't panic if this isn't absolutely crystal clear. I would expect that maybe wouldn't be exactly crystal clear, because you've never really done stuff like this, and I want you to get kind of a sense of how this works. It plants a seed for later on, when you do more theoretical stuff later on in math. Then it really does. Then you've got some prior learning to say, oh, okay, I have a sense of what this is all about, and it makes it easier to learn it later. We're not going to do a lot with this stuff. I mean, this stuff wouldn't show, for example, in the AP test. It's not like this is something that's a heavy topic in first-year calculus. But I think it's something you need to see at least once. All right, so questions on that? Okay. Why don't, man, I'm going to see if maybe I can grab a few Chromebooks. You guys can just work a little bit.